Myself, Dr. W. Gunole from Kamlani Mahavidyalaya, Nagpur. Today I am going to discuss the second part of NMR spectroscopy. We have seen the interpretation of NMR spectra. There are four important parts. First is the position, number of signal, then position of signal, intensity of signal, and splitting of signal. So already we have seen the how to find the number of signals in the compound or in the molecules. And now today we are going to discuss the position of signal, that is shielding and deshielding, and after that we are going to see the how to measure chemical shift and delta scale and tau scale, and after that we are going to see the position of signal, and after that we are going to see intensities of signal, that is proton counting. So the topic is now NMR spectroscopy part 2, and we have seen the number of signal, and the second important part of this NMR spectroscopy is the position of signal. And as we know that the position of NMR signal help us to know the kinds of proton, that is whether the proton of aromatic, aliphatic or vinylic adjacent to the some electron attracting or electron releasing groups. Each of these types of proton have different electronic environment, and therefore they absorb at different applied field strength. As we know that when a molecule is placed in a magnetic field, its electrons circulate and produces the magnetic field, and this magnetic field is known as induced magnetic field. This induced magnetic field of electron of the proton get oriented in such a way that to oppose the applied magnetic field, and in this case the field felt by this proton is diminished, and in this way proton is get to be shielded. On the other hand, in case of induced magnetic fields of the circulating pi electrons, and this in this case the when the field may oppose or reinforce the applied field depending upon the location of proton. If induced magnetic field oppose the applied field, then the proton is said to be shielded, and if it failed and or it reinforced the applied field, then the proton is said to be deshielded. So there are two, shielding and deshielding, and shielding shift the absorption peak upfield and deshielding shift the absorption peak downfield. As we know that when molecule is placed in the magnetic field, then it causes the circulation of electron surrounding the protons. This circulation of electron produces the magnetic field, that is also we know the magnetic field, induced magnetic field. This induced magnetic field may either oppose or reinforce the applied field. For example, circulation of electron in the sigma bond surrounding the protons generate. So in this slide it shows the shielding due to circulation of sigma electron present in the CH bond, and therefore here sigma bond surrounding the protons generate an induced field. This field opposes the applied magnetic field. It is shown here. So here circulation of electron, so this is the electron circulation shown here in this direction, and this is the spinning nucleus, and this is the applied H0 is the applied field, and this is the resultant field, magnetic field, which produce induced magnetic field. This induced magnetic field opposes the applied field. So this is shown diagrammatically in this field. So this is the shielding due to circulation of electron, sigma electron in the CH bond. And on the other hand, circulation of electron, in this also shown another way that in case of circulation of electron, particularly pi electron, generate induced field which may either oppose or reinforce the applied field, acting upon the proton depending upon the location in the induced field. For example, circulation of pi electrons shown in the benzene derivative produces the induced field which reinforces the applied field, shown in this slide. So in this slide there is a circulation of pi electron in the benzene. This is the benzene, and carbons are here, carbon hydrogens, and two hydrogens are shown here, and this is the applied field, and this is the ring current of this benzene ring, and there is a circulation of pi electron of the benzene and produces the induced field which reinforces the applied field, This is shown induced diamagnetic field, and this is the resultant magnetic field. So induced magnetic field reinforces the applied field. This is shown in case of benzene, and therefore here is again shown the shielding of these electrons. So here this is another example of a circulation of pi electron in case of benzene. And now similarly also we observed the circulation of pi electron of the CH double bond O bond or group, CH group or carbon-carbon double bond. It also reinforces the applied field at the proton, and also shown here of A and B figure shown in the slide. Figure A is the circulation of pi electron of the CH double bond X. X may be any oxygen or carbon. Group produces the induced field which reinforces the applied field at the proton. In the B figure is shown, this is the acetylene CH. This is the carbon-carbon triple bond is here. This is acetylene and field is applied H0. So in the figure B it shows circulation of pi electron of the acetylene produces induced field which oppose the applied field at the proton, that is aldehydic or olefinic protons are deshielded while acetylenic protons are shielded. So acetylenic proton deshielded and ethylenic or aldehydic protons are deshielded. So as we know, shielding shift the absorption peak upfield and deshielding shift the absorption peak downfield. So such shift in the position of NMR absorption due to shielding and deshielding of proton of the induced magnetic field of the electron are known as chemical shift. So again I am repeating that such shifting of position of NMR absorption due to the shielding and deshielding of proton by induced magnetic field of the electron are known as chemical shift. And so this is the important part in case of position of signal. We know the shielding, deshielding and chemical shift. So shielding shift the absorption upfield, deshielding shift the absorption peak upfield. So this shift is known as absorption peak, shifting of this absorption peak in upfield or downfield is known as chemical shift. And now in the next slide we are going to see how to measure the chemical shift of the proton. So chemical shift are generally measured by using a standard substance, and standard substance generally used in the organic molecule is a TMS. What is TMS? In short it is known as TMS. So TMS is a tetramethylsilane, and this tetramethylsilane have 4 methyl group, tetramethyl, 4 methyl groups are there, and silane, silicon. So CH4 in the same way, Si, CSC, CSC, CSC for all the 4 sides. So formula is CSC4Si. So tetramethylsilane is a standard, and for taking the chemical shift or measuring the chemical shift, a small quantity of TMS is added in the sample when we get the NMR spectrum. So this is the standard compound. As we can say it is a reference compound. Whenever we are taking NMR signal or NMR spectrum, then we have to add small quantity of TMS. So this is the by using this standard substance, measurement of chemical shift can be take place. Okay. After that, now in the next slide, now here TMS means tetramethylsilane. Why TMS is used as a standard compound? What is the reason? So here we can say that TMS is used as a reference compound because of the important 3 regions are there, and 3 regions are: number 1 shown in the slide. Number 1, it has 12 equivalent proton. Formula you know that CSC4. CSC4 means CSC, CSC, CSC. So total protons are 12. So it has 12 equivalent protons which give intense signal. Therefore, even small quantity of this compound give a measurable signal. So therefore, this is the one reason. And second important reason is that silicon is a less electronegative than carbon. Therefore, proton of TMS are there highly shielded. They give NMR signal in a region where some other protons absorb. Hence, we can say that signal of this reference compound are showing signal in the region or downfield region as compared to signal of other protons. And a third important reason is that it is inert and volatile also. this is not it cannot react with any other molecule or organic compound, therefore it is inert, and also it is a volatile, because after the excitement it can be easily removed by the evaporation after the excitement is over. So these are the reasons that we can use TMS as a standard compound. And now, as we know that advantage of using TMS as a reference is that it gives a strong and sharp NMR signal. So next slide shows the NMR signal of TMS compound. So this is the formula of TMS shown here. This is tetramethylsilane, 1, 2, 3, 4, tetramethylsilane. So this is the TMS compound, and this is the intense signal because of having 12 equivalent, 3, 3, 3, 3. So total 12 equivalent protons are there. Therefore they give a signal, intense signal at 0 ppm. Chemical shift is in a ppm. This is a upfield and this is a downfield. Generally organic molecules signals are observed in a downfield. So this figure shows NMR spectrum of TMS. It shows that proton in TMS absorb at high field strength as compared to other protons, and therefore TMS signal is used to calibrate NMR spectra. And now in the next slide we are going to see what are the scale to measure the chemical shift. Now there are two important scales to measure the chemical shift, and the first scale is the delta scale shown here, and delta is equals to, this is the delta nu in CPS, and the radio frequency used in a megacycle per second into 10 to the power 6, because we are going to find in ppm. And another scale is the tau scale. Tau value can be determined by using this 10 minus delta. Whatever the value is at delta, 10 minus delta value, we get the value of tau. So scale is shown here, how to represent the delta scale and tau scale. So here 0 tau scale in ppm values are given, 0, 1, 2, 3, 4 up to 10. So at 0 ppm TMS signal is there. So this is the reference compound. TMS is a standard or reference compound, and shown here this signal of TMS is always at 0 delta ppm, and other protons show signal in this downfield with respect to TMS. And now after that, opposite to that, tau scale, 10 minus delta. So what is now here? So it is 10, 9, 8, 7, 6 like that. So two scales have been shown, and these two scale are used to measure the value of chemical shift. And now here determination of chemical shift. One example is shown here also, that in NMR signal, that signal come at 100 CPS downfield with efforts to TMS in a spectrophotometer using a 60 megacycle per second of frequency of that instrument. So chemical shift in ppm can be determined 100 into 10 to the power 6, and the 60 into 10 to the power 6, and value is coming out to be 1.66. In other spectrophotometer using 100 megacycle per second, then the same signal will be 166 CPS downfield. So again in chemical shift can be determined 166.6 into 26, 100 into 10 to the power 6. So again value is coming 6. So this shows that ppm unit are dimensionless and independent upon the radio frequency of the magnetic field. And next slide shows, so in short we can say that in delta scale the position of TMS signal is taken at 0 ppm, whereas in a tau scale it is assigned the value 10 ppm. Small value of tau means small downfield, whereas large value means large downfield shift. On the tau scale, small value of tau means low field absorption, and high value means high field absorption. So most of the organic compound signal appear in a downfield to the left of the TMS signal, and some chemical shift value of some groups are shown in this table. So this table shows the chemical shift in the ppm of some protons. So methyl protons, and methyl protons are different types. So this is the methyl proton CST attached to C, CSC attached to CO, CSC attached to aromatic ring, CSC COR. So different protons are there. So these protons show value in delta ppm 0.9, 1.4. So these are the values shown here for different types of methyl protons. And now another proton is there, methylene, means CH2 group. So CH2 can attach here to carbon and carbon, CH2 can attach here carbon and to the ring, CH2 can attach to carbon and sulfur, so they this is the act as a CH2 act as a methylene bridge between the two atoms of different types, and they have delta value. This is having CH2 methylene, proton have 1.4, this is having 2.7, like that. So this is methyl, this is methylene, and then methine. Methine means CH group. So for this case, they are these different groups are there, and value are given here for delta ppm, and 10 minus delta ppm we get the value of tau in ppm here. So some functional group are also there, they also show here. So COH and CHO, amide, phenol, alcohol, and tetramethylserine having the 0 delta ppm value. So these are some values of chemical shift of some proton present in the different groups. Now we are going to see the intensities of signal, third important part of this interpretation of NMR signal, and that is also we can say that peak area and proton counting. Whenever the signal is observed, we have to find out what is the peak area or proton counting. So it is observed that in general quality of all NMR spectra, that area under NMR signal is directly proportional to the number of protons giving rise to the signal. So how many number of protons are present in the molecule, and it depends directly on the signal. So area, so if the number of protons are more, the area is large. So depending upon the number of proton, so we can say that here area under NMR signal is directly proportional to the number of protons giving that signal. So now another table shows that what is the area ratio under NMR signal. So in the next slide it shows that this is the table that shows peak area and proton counting. So this is methyl alcohol, and two different protons are there, two signals are there, number signal, and A proton is having A group is having 3 proton, here is 1, so 3:1. This is the ratio of proton, 3:1. So here ABC, 3 different protons are there, the ABC ratio is 3:2:1. In case of N-propyl alcohol, ABCD, 4 different protons are there, therefore they have the ratio 3:2:1. Here ABCD, D is a 1 proton is there, 3:2:1. And in case of toluene, A and B, 2 different groups protons are there, so for AB 3:5. And for paraxylene, ratio is AB and 6:4. And in case of mesitylene, 2 signals are there and A is to be 9:3. And tertiary butyl toluene, this is tertiary butyl, para-tertiary butyl toluene. Para position, this is toluene, this is para-tertiary butyl group. So tertiary butyl and para-tertiary butyl toluene have 3 ABC and 9:3:4. So this is the proton counting and ratio of protons present in the different organic compound. And now this is the NMR spectra of para-tertiary butyl toluene. And as we know, there are 3 A, B and C, 3 types of protons are there. Therefore 3 signals are there, 1, 2, 3. And now A, for the A, the signal is here shown A. How many protons are there in A? 3, 3, 3, total 9. So 9 H. Here for 9 H, the signal is, see how much it is, the height of this. So this is the this is the signal for 9H. And for now B, 3 protons are there. So for 3 proton, this is the signal for, so B for 3H proton. And C having 1, 2, 3, 4. For 4 proton, the signals are shown here C proton. So A, B, C. How the signals are shown in the NMR for para-tertiary butyl toluene. And now it is also observed that this ratio 9:3:4 can also be determined from the height of that signal. And this is the NMR spectrum of para-tertiary butyl toluene and proton counting. And now how to we have to take the ratio of this step weight. So here step weight is shown here, this weight, this is weight. So whenever the peaks are there, then there is some square brackets are there. So we have to peak ratio, we have to take a peak weight of the 3, and from this, so here the ratio of step weight ABC. So in case of A, 8.8, in case of B 2.9, and in case of C 3.8. So from this step weight ratio we can determine also the ratio of proton counting and proton ratio. And so the 3 steps are there to find out these number of protons in each group. So divide the ratio by lowest step height, then these 3 values are there and lowest value is 2.9. So divide all the 3 values by 2.9. So 3 values are being divided 2.9 and we get the ratio 3, 1 and 1.3 after dividing. And the second step is now multiply the ratio by highest number. Then here is the, in this ratio highest number is 3. So multiply it 3 into 3, 1 into 3, 1.3 into 3. So multiply it by the highest number. And then after that convert, and after multiplying we get 9, 3, 3. So here we have to convert this ratio into 9, 3, 3.9 and convert all the fractional number into the whole number. Then the ratio is there 9, 3, 4. So 9 is for, this is the ratio obtained for this compound, and here A is a 9H, B is a 3H, C is a 4H. So here we can say that the compound is a tertiary butyrylene, and proton counting by NMR can be used in assigning the structure of the compound. So again I am repeating that proton counting by NMR can be used in assigning the structure of the compound. So this is an example of para-tertiary butyrylene. So today we stop here. We have discussed today what is the position of signal, that is shielding, and de-shielding, that is chemical shift. And after that we have seen the how measurement of chemical shift, scales of chemical shift, and after that why TMS as a standard compound, and then proton counting, that is intensities of signal. And so in this part we have seen these 2 important interpretation, position and intensities of signal. In next part we are going to see the splitting of signal, different examples and the coupling constant.